Swayam Prabha. Digital India. Educated India.
Okay, so welcome to the next class of this course. So just to recap, so what we have been doing is we have started with this formulation of kinetic theory of gases, where we are dealing with large collection of molecules which are not interacting with each other, and the total energy of the system is only due to the kinetic energy of the gas particles, right? And we started and later on, especially in the last lecture, we kind of relaxed that condition, right. So earlier we assumed that the molecules are point particles, but now in the last lecture we assumed that they can actually collide with each other and they have some finite size, like we used the diameter of the molecule d. And in the last class we came up with this concept of mean free path. So we can just recap. So we defined the concept of mean free path, which is nothing but average distance traveled between two successive collisions, right. So like we assume that there is a density of these gas molecules. As they move from point A to point B, they undergo various collisions with other gas molecules, and typical or average distance it travels between two collisions we defined as mean free path, which we denoted by symbol lambda, right. And last time we saw that this lambda is basically equal to pi d squared n, and the coefficient in front of this pi actually changes the way we model this system. So if we assume that all other gas molecules they are stationary, then we have pi, but if we assume that all other gas molecules are either moving with some fixed velocity, say v rms, or there is a Maxwell distribution, so this coefficient changes, right. So it so it's I think it's square root of 2 and 4 by 3 respectively in those two cases. But the important thing is that the mean free path is like proportional to this factor, right. So as you increase the density of gas molecules, it's very natural to see that the lambda will go down, right. And so does if you increase the size of your molecule, there will be more collisions and your lambda will go down again, right. And also later on we saw that the way these lambdas or these typical free path distances they are distributed is as follows. So n equals n0 e raised to the power minus x by lambda, where n is the number of gas molecules which avoided collisions after travelling a distance x, right. And we saw that these distances they are exponentially distributed, right. So it's exponentially unlikely for a gas molecule to avoid a collision after travelling certain distance x. Okay. So essentially what we will do in this class is we will basically going to break down few more assumptions that we made, right. So if you remember, okay, so like I said, the first assumption that we made initially was that gas molecules they don't have any dimensions, but when we broke that assumption, we relaxed that assumption, we came up with this concept of mean free path. But there were other assumptions also which we made. One was that the gas molecules they are moving in all directions randomly with equal probability. There is no density gradient in the collection, like it's equally likely to find a gas molecule everywhere in the container, as well as the system is in equilibrium, right. So what we will do is we will one by one kind of break or relax these assumptions, and we will see how we can basically understand certain what is known as transport properties of these systems when they are driven out of equilibrium, right. So, basically what we will do in this class is we will drive or we will consider gases driven out of equilibrium. Right. And maybe I can quickly summarize how we can do that. So, say you have this gas which is in 3 dimensions. So, this is z axis, say this is x axis, this is y axis, right. So, earlier we assumed that these gas molecules are equally likely to be found everywhere, right, in space. But first, so there were three assumptions that we made. Molecules move randomly in all directions, right, which means their velocity vectors, if you sum it up, you will get 0, right, at all locations in the space. The second assumption was the gas is at equilibrium, right, which means the temperature or rather average kinetic energy of gas molecules is uniformly distributed in space. All that means was, if I calculate the average kinetic energy of gas molecule moving in one corner and in the other corner, that is same, which means there is no temperature gradient, right. So, the kinetic energies are equally distributed, like uniformly distributed in space. And third assumption that we made was it is equally likely to find a molecule everywhere, right, everywhere in space, which means in any spot in the space the density of gas molecule is same, right. So, there is no density gradient as such. And what we will do basically in today's class, we will basically break down or relax these assumptions, and we will see there are certain transport properties. For example, if we assume there is certain spot in the space where gas molecules are all moving in one direction, we will see that will lead to a net transport of linear momentum along a certain axis, and that will lead to a very macroscopic property of the system, which is known as viscosity, right. So, maybe so when we break down this assumption, like so assumption number 1, so we come up with the concept of viscosity. When we break down the assumption that that kinetic energies of gas molecules is not uniformly distributed, this leads to a very important concept known as thermal conductivity. And when the gas molecules are non-uniformly distributed in space, there is a coefficient of diffusion, right, diffusivity or coefficient of diffusion. Okay. So, that is what we are going to do in today's class. All right. So, let us start with point number 1. So, first one is basically transport of momentum, or maybe viscosity, coefficient of viscosity. Which is a result of transport of linear momentum. Okay. So, let us see how we can understand that, all right. So, again so consider we have like this 3-dimensional space. So, let us say this is z axis, this is x axis and this is y axis, right. And what we are going to assume is that in the x z plane, and if we just take sorry in the plane of x y, okay. So, there is this plane which is in x y plane. So, at any given moment the gas molecules, okay. So, say there are 3 planes, okay, and there is a velocity gradient, okay. What do I mean by that? So, all the gas molecules in this plane on average they are moving with certain velocity v. So, let us call this plane 2, or maybe I can write here. So, let us call this plane 2, but molecules in plane 1 they are moving with slightly higher velocities, right, speed. So, this is v plus lambda times dv by dz, right. So, the gradient is along z axis. So, the speed of molecules in this plane is slightly greater than v, and the coefficient that comes in front of this term is the mean free path, right. And similarly, let us assume the molecules moving in this plane they are moving slightly slower, right. And typically these planes are separated by a distance lambda, right. And remember what is lambda? Lambda is the mean free path, right. That is the distance over which typically molecules they collide with each other. And the reason we picked lambda is because if molecules are much closer to each other than lambda, right. So only then they will undergo collisions, right. So, if they are very far away from each other they will not undergo collision. So, there is natural length scale in the system which comes due to this mean free path, right. So, let me write. So, okay. So, here lambda is mean free path, right. So, essentially what we have is we have a velocity gradient in the system, right. For some reason, say we have driven the top part of the collection of these molecules with certain speed, and there is and we have introduced a gradient in the speeds, okay. And now you can assume you can like believe you can now visualize that these molecules which are moving much faster than molecules in the plane number 2. So, they will like collide with these molecules, and they will basically transfer certain momentum from this direction to this direction, right. Similarly, since molecules moving in plane number 2 they are moving faster than molecules in, let us call this plane number 3, there will be maybe I can use different color. So, there will be a net transfer of momentum from this direction to this direction, and also from this direction to this direction, right. So, let us call this plane 3, and the red arrow means transfer of linear momentum, right. Because system will so say you drive the system, it will tend to achieve another equilibrium state where the velocities are again evenly distributed, and that will only happen when there is a net transport of linear momentum along z axis, right. Okay. So, basically maybe I can write few things. So, so what we have is we introduce a velocity velocity gradient along z axis, which is equal to dv by dz, right. So, the velocity is changing along z axis. So, this gradient is along z axis, right. And as a result, like I said, these molecules they will collide with slower molecules, and they will impart some momentum to these molecules. Similarly, molecules moving in plane 2 will impart molecules moving in plane 3, and therefore, there will be some sort of resistance, right, which will naturally come into this system, and that resistance is known as viscosity, Okay. So, let me define it a little bit better. All right. So, so what I am saying is, okay. So, like I said, there is a change in momentum along z axis. So, what we can actually see is that so rate of change of momentum okay all right, that should be proportional to the magnitude of this gradient, right. So, that would be proportional to dV by dz, all right. So, okay, maybe we can define it in this way, rate of change of momentum or okay. So, let me define it little bit better. So, this should be okay. So, change or transfer of momentum, I mean linear momentum per unit area per unit time. Okay. So, how quickly this transport of momentum is happening and what is the magnitude of it per unit area, that should be proportional to dV by dz, right. So, if you have a strong gradient, there will be much larger amount of momentum transfer, right. And what we can write is that, so left hand side, which is this term, right, I am not writing this, is equal to eta times dV by dz. Okay. So, eta is just a proportionality constant, right, and it is known as viscosity or coefficient of viscosity. Okay. So, there is this so this resistance that is felt by these gas molecules, which can be measured using this term that we have defined as coefficient of viscosity. Okay. So, now basically our job is just to calculate or evaluate the value or the amount of this momentum transfer between two plates and find out the expression for viscosity, all right. Okay. So, we are going to make a small assumption. Okay. So, remember we said that gas molecules, they are moving randomly in space, right. So, there is no net preferred direction, and something that we have broken here, right. So, we are saying there are more molecules which are moving in this direction in plane 1 than in plane 2, right. But if we assume, so okay, and also okay. So, let us let V RMS is the root mean squared velocity or speed of molecules, right. And as you know, this is basically given by square root of 3 k B t divided by m. Okay. So, if the net average speed of these molecules moving in plane 1 or the quantity, if this V is much smaller than V RMS, okay, in that case we can continue to assume that the gas molecules are still randomly moving in each direction, right. So, remember we have so also we have n, the variable, which is the number density, right, which is total number of gas molecules per unit volume. So, and we have six directions, right. So, there are these directions in which gas molecules can move, and on average there are n by 6 per unit volume molecules moving in say plus z direction, n by 6 moving in minus z direction, similarly n by 6 moving in plus x direction, n by 6 moving in minus x direction, and same thing with y axis, right. So, on average even if we have broken this condition that molecules are moving randomly, but since this V, the net transport of momentum along any plane is much smaller than the average root mean squared speed of these gas molecules, they are still n by 6 number of molecules moving in any given direction, right. Okay. So therefore, so what will be, okay, so okay, so therefore number of gas molecules crossing any plane per unit area per unit time, what will that be? Okay. So remember, n has dimensions of inverse volume, right, and if I multiply this this small n with Vrms, right. So what I am saying is what is the net number of gas molecules which are moving, which are crossing any plane, right. So that per unit area per unit time, that will be equal to n, which is the number density, times root mean squared velocity, right, and this has dimensions of number per unit area per unit time. Okay. You can very easily check that. All right. So therefore, so what will be, okay, so next step is so okay, so what is the linear momentum of gas molecules moving along one, right. So okay, so let me write, okay, so since okay, so remember, so the molecules in plane 1, they are moving at slightly greater momentum than molecules in plane 2. So there will be net transfer of this momentum per unit area per unit time, and you can see you can very easily see, okay, so net transfer of momentum between plane 1 and 2 per unit area. So let me, okay, per, so let me just write per unit area per unit time, okay, just a shorthand thing. So this will be okay, sorry, this will be n by 6, right, because I said there are 1/6 of number of gas molecules moving in any given direction, right. So that will be n divided by 6 multiplied by mass of molecule multiplied by the speed of those molecules, which is basically so okay, times so V plus dV by dz, sorry. Okay. So that will essentially be given by n by 6 times m times Vrms times lambda dV by dz minus V, right. So this is the amount of momentum transfer from plate 1 to plate 2, plane 1 to plane 2 per unit area per unit time. Okay. So similarly a net transfer of momentum, maybe it's, I can just write from, right, from plane 2 to plane 3. So remember, plane 2, if there is a positive gradient, it is moving faster than plane 3, right. So again there is a net transfer of momentum from in the downward direction, and that will also be equal to n by 6 m V RMS times V minus lambda dV by dz. Okay. And you can see this is basically, so this V cancels out. So we have n by 6 m Vrms lambda, maybe I will just need little more space. Okay, let me make little more space here for myself. So V plus lambda dV by dz minus V, right. So V cancels out. So we have n m Vrms lambda dV by dz divided by 6, right. And you can see this in the second case, this term is also same, right, m Vrms and this V cancels out. So, minus minus becomes plus lambda dV by dz. Okay. So, what will be the total momentum transfer? That will be this plus this, right. So, therefore, total transport or transfer of momentum through plane 2 per unit area per unit time. Okay. So, this is just a way of writing that. So, that is basically sum of these two terms, and it will be n by 3 m times V RMS times lambda times dV by dz. Okay. So, again, so then what will be the coefficient of viscosity? So, remember the coefficient of viscosity is nothing but transfer of momentum per unit area per unit time divided by the magnitude of the velocity gradient, right. So, therefore, eta simply becomes this term divided by dV by dz, right. So, that just becomes n by 3 m times V RMS times lambda. Okay. So, dV by dz gets cancelled out, and this is known as, okay. So, this is one of the results, this is coefficient of viscosity. Okay. All right. So, remember now we know what is our VRMS, right. So, VRMS is basically 3 times kBT divided by m, and also lambda, as we saw in the last class, is basically 1 by pi d squared n, where n is the number density. Okay. And if we plug these substitute these values here, therefore, our eta basically becomes maybe you can okay. So, this becomes n by 3 times m times 3 kBT divided by m times 1 by pi d squared n, and if you just do little bit of simplification, you can see that this is nothing but equal to square root of m kb square root of t divided by pi d squared. Okay. So, the important result here is that for ideal gases, okay, so remember this is still true only for gases, right. We are still assuming there are no intermolecular attractive forces, right. So, this is still in a very much in a gaseous phase, right. So, for gases, the coefficient of viscosity has to scale with square root of temperature, and also eta is independent of pressure, right, is independent of pressure. Okay. And of course, these are actually found out to be true within reasonable range of parameters. Of course, there will be breakdown if we increase, if the pressure of the gas is very high, in which case the intermolecular distance can be very small, and there can be intermolecular interactions which can start playing a role, right. But if you are at reasonably low density and at reasonable pressure values, then it turns out your viscosity indeed scales with T raised to the power 1 by 2. Okay. So, I will not really go down into the breakdown of this expression, but under ideal conditions we expect viscosity to increase with temperature with the power of 1 by 2. Okay. But very quickly what we can now do is we can compare the coefficient of viscosity. You know, like we encounter water every day, and water has certain viscosity, and when I say water, I mean water in liquid phase, liquid state. But say you boil the water and it goes into gaseous phase, which is the steam or vapor. So, then it will have its own viscosity. Okay. So, now we can very quickly check what is the viscosity of water in gaseous phase as compared to water in liquid phase, right. So, remember we now have this formula of eta, which is 1 by 3 1 by square root of 3 times this thing, and now we can very easily we can plug all the values that we know for water molecule. So, for example, eta of H2O in gas phase, okay. That will be, maybe I can write down this again, square root of mkb T by 3, okay. I am just rewriting this formula, times 1 by pi d square, okay. So, if we use mass of water molecule to be something like 3 into 10 raised power minus 26 kilogram, and the size of the water molecule to be 2.75 angstrom, which is minus 10 meters in SI units. If you plug this here and use the value of Boltzmann constant, and let us say the temperature is like 400 Kelvin or something like that, right, where you are in a gaseous phase. So, in this case you get viscosity of water to be around 10 raised to the power minus 5, okay. So, this is just a ballpark figure. So, this is Pascal second, all right. So, this is gaseous water, okay. And the next thing that we can see is how does it compare with the viscosity of liquid water, right. And we know that viscosity of liquid water is actually equal to 10 raised to the power minus 3 Pascal second, okay. So, this is liquid water. And you can very easily see that in gaseous phase the viscosity is 2 orders of magnitude smaller than in liquid phase, right, and which is very natural to believe or imagine, because in liquid phase gas molecules are much tightly packed, they are close to each other, and there are considerable amount of intermolecular interactions, right, and that will lead to much efficient momentum transfer, right. So, if you flow water, it will provide much more resistance to flow when in liquid phase as compared to the gaseous phase, okay. So, that was about the first thing that we saw. So, basically the molecules moving randomly in all directions, right. So, where we said if we break down that assumption, we have coefficient of viscosity. So, now let us see what happens if we have temperature gradient in the system, right. So, basically so we had first, now we can go to second, okay. So, second is basically let us see how I, yeah. So, coefficient of thermal conductivity and this is basically, like I said here, it is transport of linear momentum. Now, we have transport of energy, or as you know, transport of energy is nothing but heat, right. So, if you have heat transfer in the system, that leads to what is known as thermal conductivity coefficient, right, which is a property of a gas, okay. So, we will basically set up the problem in the similar way like we did for the viscosity, right. So, you have z axis, you have x axis, you have y axis. So, rather than having the velocity gradient, now say we impose temperature gradient, right, which means the magnitude of velocity of molecules moving in plane 3, 2 and 1 is different, right. So, what I mean is, so say this is your plane 1, plane 2, plane 3, they are again separated by typical distance lambda, right, and the temperature of the gas molecules in this plane is T plus lambda times dt by dz, where dt by dz is the temperature gradient along z axis. So, this is temperature T and this is T minus lambda dt by dz, okay. And along the similar lines, we can define heat Q, and what is heat? It is just the transfer of energy, right. So, let us define Q as a heat passing per unit area per unit time, right. So, what is the amount of energy transfer in certain direction per unit area per unit time, and again we can like imagine that this Q has to be proportional to the magnitude of temperature gradient, right, and this will be minus dT by dz. And why minus? Because heat will go from high temperature to low temperature, right. Okay. All right. So, and if we want to remove the proportionality sign, this just becomes minus k dt by dz. All right. Okay. So, now basically we have to do the same okay. So, here the k is known as coefficient of thermal conductivity. Okay. So, again we are going to assume that the amount of gradient value or the change in temperature along in space is much smaller, very low. So, that still equal number of molecules are moving in space, right. So, we are again going to assume that along all these directions there are n by 6, n by 6, n by 6, n by 6, 6 number of gas molecules per unit volume moving in any given direction. Okay. And also we know average kinetic energy of gas molecule at certain temperature T is basically 3 by 2 kBT, right. So, therefore, we can now see that so energy transfer which is nothing but heat, right, energy transfer from plane 2 to plane 1 is basically okay, and also again per unit area per unit time, okay, that is important. So, that will just be equal to n by 6 times V RMS, right. This is the number of particles, number of gas molecules moving per unit area per unit time multiplied by the energy, right, 3 by 2 kb, and the energy difference, the temperature difference here is T plus lambda dt by dz minus T, right. So, this is, so again I can do, so this is the heat transfer from plane 1 to plane 2, right. So, similarly I can do the same thing between plane 2 to plane 3, right, and that will also be n by 6 V RMS times 3 by 2 kb times T minus lambda dt by dz. Okay. And that transfer will also happen in this direction, right. And therefore, what will be the total heat transfer, net heat transfer, that will be just sum of these two, right. So, therefore, Q will be n by 3 times V RMS times 3 by 2 kb times lambda dt by dz, right. And since k, which is the thermal conductivity, that is Q divided by the magnitude of temperature gradient, right. So, this simply becomes, so this 3 cancels out. So, we have n by 2 V RMS times kb times lambda. Okay. So, again we can what we can do is, so since V RMS again is 3 kBT by m and lambda is 1 by pi n d squared, right, and if we plug these values in, so we get k equals 1 by 2 square root of 3 kBt divided by m times kb times 1 by pi d squared, because n will cancel out. Okay. So, this n from lambda will cancel with this n. And remember, we also had a form for the viscosity, coefficient of viscosity, which also had similar looking terms, and if we just substitute this value of viscosity into this relationship. Okay. So, you can very easily see that 3 by 2. So, this is nothing but equal to 3 by 2 eta divided by m times kb. Okay. So, what I have done is substituted eta equals the expression that we had, which is 1 by square root of 3 times square root of m kb t divided by pi d squared, right. Okay. This is what we obtained here. Okay. This is what we obtained here. Okay. So, what that means is the coefficient of thermal conductivity is basically proportional to the coefficient of viscosity, right, and therefore, K should also scale with square root of temperature, and independent of pressure. Okay. So, these are the so this is what we can so this is how we can basically make sense of these properties of these of these gases in term by just working out so this expression, right. So, this is a way of understanding the transport properties of ideal gases through the formulation of kinetic theory. All right. And the last thing that we will do is we will now break down the assumption that gas molecules are equally distributed in space. Okay. So, basically the third thing along the similar lines is coefficient of coefficient of diffusivity, or which is okay. So, coefficient of diffusion, which is transport of matter, right. So, coefficient of diffusion which comes due to transport of matter. Okay. And again, what we are going to do is, say we have a, so this is z, x and y, okay, and along plane 1, okay, say the local density of gas molecules is n plus lambda dn by dz, where dn by dz is the density gradient along z axis. In plane 2 the density is n, and in plane 3 the density is n minus lambda dn by dz, okay, and the typical spacing between these planes is lambda. Okay. And again now what is happening is we have lot more molecules in one part of the container than the other, and these molecules and this is like out of equilibrium, right, this is not the equilibrium state. So, these molecules will basically tend to spread out evenly, right, and that will lead to a diffusion, right, and we can define a coefficient of diffusion corresponding to that, right. So, therefore, we can again define a quantity which is number of gas molecules moving per unit area per unit time. Okay. So, the gas molecules passing through space per unit area per unit time, which is the diffusion, right. So, which leads to the net transfer of these gas molecules, that again will be proportional to the magnitude of density gradient, right. So, dn by dz. Okay. And to remove this proportionality sign, we can just define it as d times dn by dz where d is the coefficient of diffusion or diffusivity, right, of diffusion, and also known as diffusivity, okay, or simply diffusion coefficient. Okay. So, again what will be again, so remember there are more molecules here, there are fewer molecules here. So, there will be on average net transfer of molecules from plane 1 to plane 2 to plane 3, right. So, there will be a transport of matter molecules from plane 1 to plane 2 and also from plane 2 to plane 3, right. So, therefore, V RMS by 6 times n plus lambda dn by dz minus n plus so this is from plane 1 to plane 2, and for plane 2 to plane 3 we have V RMS, sorry. So, V RMS by 6 times n minus lambda dn by dz. Okay. So, these terms cancel out, this becomes plus, and we end up with 1 by 3 V RMS times dn by dz. Okay. So, this is the number of gas molecules moving per unit area per unit time, and if we divide this by the magnitude of density gradient, so we can write the final expression of diffusion coefficient, which is 1 by 3. So, there is a lambda here, 1 by 3 V RMS times lambda. Okay. So, this is what the coefficient of diffusion looks like. All right. But remember, we saw that viscosity is basically given by n by 3 times m times V RMS times lambda, right. So, since viscosity eta, right, where the coefficient of viscosity is 1 by 3 times m times n times V RMS lambda. Okay. So, therefore, d simply becomes, so what I will do is I will just substitute for lambda from this expression. So, this just becomes 1 by 3 times 3 eta divided by m n, right, and this is nothing but eta divided by m n, right. And what is m? M is the mass of one molecule. What is n? That is the number density. So, therefore, m times n is the mass density, and let us call that rho, right. So, where rho is the mass density. Okay. So, therefore, another expression for the coefficient of the diffusion coefficient is eta divided by rho, right. And also what we can do is we can now we can again substitute for lambda and V RMS. Okay. So, also since V RMS is square root of 3 kBt divided by m, and lambda is 1 by pi and d squared. Okay. So, therefore, the d basically takes this form. So, if you just substitute that, so you will get kBt divided by 3 m n squared pi squared d4. So, I have just moved everything inside the square root. Okay. Or more conveniently I can write it as follows, square root of, okay. So, or most importantly we can see from here that d scales with square root of temperature divided by n, right. And we know from ideal gas equation P equals n kBt, right, where n is the number of gas molecules per unit volume, right. And if we just plug n, which implies n is P by kBt. So, if we just plug that here, so we can see that this scales as square root of t. Okay, maybe I can. Okay, so this is nothing but T raised to the power 3 by 2 divided by P. Okay. So, from this calculation we expect the coefficient of the diffusion or diffusion coefficient to scale with 1.5 power of temperature, and it should be inversely proportional to the pressure of the gas. Okay. So this is basically the end of the class. So, what we have done is we have basically relaxed few assumptions, very strict assumptions that we made in the kinetic theory, and we very conveniently we drove the gas out of equilibrium, and due to that, depending upon how you introduce the non-equilibrium condition in the gas, you get various transport properties like coefficient of viscosity, thermal conductivity and diffusion, and we have evaluated the expressions for them. Okay. And in the next class we will basically look at under what conditions the kinetic theory breaks down. Okay. And eventually that will lead to what is known as real gas equation, right. So, we derived ideal gas equation, but in the next class we will look at the real gas equation. Thank you.